Okay, so welcome back. In this lesson, we're going to talk a little bit about how we actually go and we apply our whole ideas of sketching so that we can understand how the transformations take place on the trig curve. So we talked a little bit about some important vocab on our trig curves, okay, and the features that we use them for. So in this particular case, we're just going to get straight stuck into it. I'm going to teach you a method that sort of allows you to ensure that you're not going to make mistakes when you're going through and graphing trig curves. Okay, it's not the fastest, but it does work in pretty much every scenario, and it's a nice little tool to have. So first things first, let's go through and we're going to examine our trig curve here. The first thing that we would like to do, we'll notice that it's basically our normal cos curve, which means that almost everything's going to be the same except for the fact that our amplitude has been changed. So our amplitude in this particular case is equal to 3. So it's 3 from the center. Okay, so that's our vertical dilation there. Okay, so a scale factor of 3. So our center in this particular case, it's a normal cos curve, hasn't been shifted up or down. It's going to be 0. And the reason we know it hasn't been shifted up or down, there's no number on the end added on or subtracted. Our period, okay, is still the same. We haven't horizontally dilated it. So it's still 2 pi divided by 1. 1 being the number that's attached in front of the x, okay? So it's going to take one cycle to complete. One rotation will occur inside of 2 pi. And then the phase or the horizontal translation is just equal to 0 because we have nothing happening on the inside of our function with our x. So I hear you ask, how do we go and sketch things that have been transformed? Well, for a cos curve, the easiest thing to do, okay, is to go and pick 5 points from the original curve. So the points that I've picked are the peak, the intercept, the trough, the intercept, and then the next peak, keeping in mind that our cos curve does that. So there are our five important points. And what I'm going to do is I'm going to transform each one of them based over what's happening over here, okay? So given the fact that we have our amplitude being 3, that means our curve has undergone a vertical dilation scale factor of 3. That only affects our y-axis, okay? So what that means is our intercept is going to remain the same, but now our y values all get multiplied by 3. So it becomes 0 and 3, pi on 2 and 0, pi, and now multiply the y by -3, we get -3, 3 pi on 2 and 0, and finally 2 pi, keeping in mind the x values don't change, multiplying the 1 by the 3. Okay, now that we have that, there are our 5 key points that we can go and put on the graph to get a bit of an idea of how everything's going to work. Okay, so I would go ahead and I would mark out -3 and 3, and that comes from the fact that we can see that that is our max and our min, okay, from the translation, okay, oh sorry, from the dilation, my apologies. So at 0 and 3 we put our first point. Then at pi on 2 and 0, that's our first intercept. At pi, we get -3. And then at 3 pi on 2, we get 0. And then at 2 pi, we get 3. And then it's just a matter of connecting the curves together in a neat way that communicates our understanding. Keeping in mind here, okay, what's actually happened is the fact that we've just gone and we've essentially blown up our trig, our cos graph in the vertical direction like a balloon. Now, okay, you'll notice I haven't really changed the scale on my graph. It's much easier for you to get a basic foundation to draw the trig graph, okay? The only time that you want to try and change the overall shape is if it's really, really complicated. Even then, change the scale if you can, okay, that runs along your horizontal and your vertical axes, okay? And that way, it'll help you sort of keep track of everything in terms of the transformations. All right? Okay, so let's do another. Just before we move on, I should actually address the fact that we haven't fully answered the question. It's also asked us to state its range, okay? So for this particular graph, we're going from -3 to 3 inclusive. So our range is going to be from -3 to 3 inclusive of those brackets, and it's always a good idea to go and nominate that with our notation, okay? All right, so let's have a look at another curve. So on our next example, we're going to talk about a horizontal dilation now. Now, I've already written some stuff out ahead of time, but I'd like to just sort of point it out as we go. So we're going to graph, the question asks us to graph this curve, sine of 2x, okay, which you would have done in year 11. Okay, but now we're just going to put it under a different lens and also describe its transformation from y equals sine x. So we like to think that is our original function, okay? So it's handy to understand what's going on here. We say that y equals sine 2x is a horizontal dilation of the original function and that it has scale factor 1/2. Remembering that when I do a horizontal dilation, if I multiply the inside of the function, what I'm actually doing to each point is I'm dividing by 2. And what that comes down to is the fact that we have essentially calculated what's happening to the x before the function itself is executed. Okay? All right. So something that's also worthwhile noting that you don't actually have to go and calculate inside of this, okay, is the period of the function. Remember, the period of sine is 2 pi divided by n, where n is whatever number is attached in front of the x. So the period in this particular case will be 2 pi over 2, which is just equal to pi. So every single pi, okay, we're going to have a complete and total sine graph. So that means if we're to graph this from 0 to 2 pi, which we will in just one moment, we're going to have 2 cycles. Okay? So, like before, what we're going to do is we're going to start sketching, okay? And I'm going to encourage you to use the table method that I showed you in the last example. Again, with 5 important points. In this particular case, our 5 important points are this. 0, 0 for the first point on the sine curve. If you're not sure, you can pull the sine curve up in front of you. Then at pi on 2 and 1 will be our next important point. At pi, 0 is our next one. 3 pi on 2, and that will get us -1. And then 2 pi and 0. Okay? So there are 5 important points that we want to work with. That's from our original. Now let's do our horizontal dilation. That's going to affect the x values in each of these. And the way that it's going to affect it is from the scale factor. So each of the x values, we're going to multiply by 1/2. Okay? So we end up with 0 times 1/2 is 0, and that gives us 0, 0. Pi on 2 times 1/2 is pi on 4. And 1, we don't affect the y coordinate. Pi times 1/2 is pi on 2. 3 pi on 2 times 1/2 is 3 pi on 4. And then 2 pi times pi is just pi. Now you might be thinking, hang on, we have to sketch this for 0 to 2 pi, but I only have the values from 0 to pi here. Well, that's not a problem, because what it means that we're able to do is we're able just to repeat the pattern that's occurring in this line here all the way throughout, noticing that we're going up by essentially quarters in each of the aspects of what we're doing, okay? Alrighty, so let's have a little bit of a look at what's going to happen, right? So our first point is going to be here at 0, 0. Our next point is going to be at pi on 4 and 1, okay? Noticing how I've set my scale up here for success to avoid me having to do really, really complicated graphs. Then at 3 pi on 4, I end up at -1. Okay, then back up to pi is 0, 5 pi on 4 is 1, 3 pi on 2, okay, which is the same as me saying 6 pi on 4. Okay, we end up back at 0. 7 pi on 4, we're here at -1, and then again at 2 pi. And that agrees with our period that we were talking about happening every pi. So as you can see, all right, inside of pi, the graph occurs once and then again. All right, now we've got to put everything together. Now it's just a matter of being neat. Okay, keeping in mind that I've kept the scale to my benefit so that when I go through and I sketch, everything's a little bit easier. Okay, all right. So that's how we go and we graph things with a horizontal dilation. Okay. Okay, so